Today we start a new chapter on design and analysis of bioreactors, and this chapter in a way brings together much of what we had done in the last part of the course. And the reason I am saying that it brings together much of what we had done in the last part of the course is because we had looked at fundamental processes. So we looked at the kinetics of enzyme, we had looked at the effect of mass transfer on that kinetics, we had looked at growth, cell culture and cell growth, we had looked at the effect of mass transfer on cell growth, we had looked at the effect of inhibition and so on, on cell growth, inhibition and multiple substrates and so on and so on. But these are all fundamental processes we looked at. But what happens to these fundamental processes when you bring them together into a real system? And that is a thing that we are going to study. So, what is a real system? Because if you are trying to culture a cell, you would need, on a large scale, you would need a bioreactor. Now, the bioreactor could be either a batch type of reactor where you put in the stuffs, okay, and let it be there for a day. So, put in the stuffs means put in the cells that you need to that you are trying to incubate, put in the nutrients, allow it to stay there for a day or so, and then you generate the product. So, that could be a batch system, or it could be a continuous system, that is the feed, that is the nutrients, and the cell is coming in and it is going out at a continuous rate. Now, that continuous rate could be a very slow rate, So, the residence time in the system of the reactor could be of hours and could be of the order of a day even. It could be a very slow rate, but still you can have a continuous system. So, these are the two different kinds of bioreactors that we are going to talk about, but what I am trying to say is that these bioreactors bring in all the fundamentals. They bring in the kinetics, the cell growth kinetics, the effect of inhibition, effect of substrates, and so on. So as a result, what happens is that any real system, when it brings in all the complicated kinetics and everything, turns out to be a little more complicated than the fundamental systems that we had studied. So, as a result, this is slightly more complicated than what we had done before. Today's lecture is going to be straightforward and simple. It is on just the design of bioreactors, but when we go into the analysis of bioreactors, you will see, because of these different factors coming in, for example, the substrate and the cell concentration, and we may or may not even look at the effect of inhibition, but when we do, it is a lot more complicated. The effect of inhibition, the multiple substrate, because of all of these coming in at the same time in a real process. Okay, till now we are looking, as I said, we are looking at only kinetics or mass transfer as a theme or a subject of study, just as something that of theoretical interest. But now we are trying to understand something which is of engineering interest, and this is a very engineering aspect of the course, where we are trying to understand and quantify how much cells are going to be produced and what is the amount of substrate. So, very basic things. What is the amount of substrate that we need to put? What is how much cells are going to be produced? What should be the size of the reactor? What should be the residence time in the reactor, or in other words, what should be the size of the reactor? If it is a batch reactor, what should be the time we should give? These are questions that we will try to address, and those would be coming in the analysis part starting from the following lecture. Today's lecture, as I said, is straightforward, and let us start it. It is called Design and Analysis of Bioreactors. As I said, that the two kinds of reactors we are going to look at are batch reactors and CSTRs, continuous stir tank reactors, and the stirring has to be slow, because you do not want a very high stirring rate in these reactors with cells. So, if you write a batch reactor, you have studied batch reactors before. So, if you write a batch reactor, what would be the balance of a batch reactor? What kind of balances you need to write? It's just what's that? It's just volume balance and the product, one for the concentration of the product. So, this is the balance for the concentration of the product. As you can see over here, so ddt of Ci times V is V times R, R being the reaction rate, and R is a function of Ci and Cj, that is all components, fine. Now, if V is a constant out of that, so if when is going to be a constant, is going to be a constant if it is a liquid phase reaction, because liquid phase reactions typically do not change volume much. Even if they change because of molar increase, it is not appreciable. So, if volume is a constant, then you can take it out of the differential and cancel it, and you will get dC dt equals R of C. Okay. So, this is the total volume balance. So, this is the balance for the particular component Ci, and this is the total volume balance, rho being the density. For a constant volume constant density system, this whole term would be 0 and you can take V out of the system. Okay. So, this is for liquid reactions or constant volume constant density systems, typically more or less constant volume and actually constant density systems. So, you can take it out of the differential and you can write dc dt equals R of C, right. And then you can add in a thermal energy balance if you want, which is if the temperature of the system is changing appreciably. Typically it does not change appreciably, the reason being there is a range of temperature within which the system has to be maintained, and you try to maintain it typically within a small range. Within that small range the changes are not large, and the reason the changes are not large because these growth reactions that take place do not have a very high activation energy, they do not really have the heat of energy is not really very high. So, typically we neglect the thermal balance, but if to be on the safe side and to be theoretically very correct, if you want to write a thermal balance, then this is how it looks like: rho times V times Cp and dt dt. So, rho being the density over here, okay, V being the volume of the reactor, Cp being the specific heat of the mass of whatever is there in the reactor, the liquid average specific heat, T being the temperature and little t being time, minus delta HR is the heat of reaction of the growth reaction that is occurring. So, these are essentially any kinds of reactions could be any kind of reaction, but what we are looking at essentially is our growth reaction. So, we are trying to culture cells over here, R being the reaction rate for the rate of culture, V is again the volume, Q is any kind of heat source or sink that could be there in the reactor apart from what's happening in the reaction. So, apart from the heat of reaction, if there is any other kind of heat source or sink inside the reactor, Q is that, and W is the work done by the reactor. This is a basic thermodynamics model, I am sure all of you are aware of. So, now the reaction rate. So, we had the reaction rate over here R, and what should be the reaction rate. Now, as I said that these equations are very basic equations and you can use them for all kinds of reactions that happen in bioreactors, but we want to specifically look at, we are specifically interested in growth reactions, and we will use today the very simplest kinetics of growth, monode kinetics, and through much of this chapter we are going to use monode kinetics, but you should be ready to deal with other kinds of kinetics, because in the test that is what I might give you, with inhibition, like we did with inhibition, with multiple substrates. So, what happens when you put these kind of kinetics, it gets a lot more complicated, the whole analysis, and you should be ready to do those kind of things, I tell you in advance. So, the monode growth model. So, you are aware of the monode growth model. So, dx dt is mu x times mu x, where mu is given as mu max times s over ks plus s. Okay. Now, let me ask you this: is this equation that I wrote for the monode growth model, is this valid for all kinds of reactors? Del x del t, whatever is on the screen, del x del t equals mu x. Is that valid for all kinds of reactors, or is it valid for a specific kind of reactor? Residence time is very large. No. In the limit of residence time going to infinity, this is valid, not very large, but that is a too theoretical answer. Why don't you give a more practical answer? That is correct, but that is a very theoretical answer. So, why don't you give a very more practical answer to that? When is that valid? When is it valid for, see, the kind of reactors we are used to are let me go through this a little bit, and I wish I had. So, batch reactors, I think this is an interesting thing I do when I bring all the details of the notes. So, reactor types. then okay. So these are the 4 reactor types you are aware of. Now what I want you to tell me is that I am not sure if you know, but you can make a try, that which out of these 4, which was the first reactor that was discovered? Batch reactor. When was it discovered?
It was used in fermentation. Means 18 or 1600.
Well, the batch reactor was the first reactor to be discovered, that's true, but it was discovered at not at 1800, it was discovered at the beginning of human civilization. You know, cooking, for example, is a batch reaction. So if you think that way, and so there is no exact account of when the batch reactor was discovered, because everything that had been there had been a batch process till now. Okay, so the batch reactor is the most common, most natural of human reactors that had been used all through the whole of human civilization. As I said, that fermentation came in much later. Cooking, the very basic human activity that started at the dawn of human civilization, is essentially a batch reaction that occurs, right? So that's true that batch reactor was in this around. So let's say history of reactors, batch reactor was sort of dawn of civilization. The second one is a plug flow reactor, okay, PFR. This is how we'll refer to it, plug flow reactor. This was developed in the early years of the 20th century, so around 1900, just after 1900, okay, just after 1900. I think 1905 or something like that. Do you have any clue who could have discovered the plug flow reactor? It was discovered by, guess? Yeah. It was discovered by Langmuir. Forget the year, around 1905 or something like that. 5 to 8, I think around 1908 or something. Langmuir is the first and only chemical engineer to get Nobel. Okay, he's the first and only chemical engineer to get the Nobel Prize. What did he get the Nobel Prize for? Do you know? The Langmuir initial isotherm. Yeah, the Langmuir isotherm. So but he was the one who discovered this. Now, the plug flow reactor was useful. Again, why was it useful? Because till then processes were batch, which means that you put them in and wait for 4 hours, 6 hours, 12 hours, 24 hours to get the output. So which meant that during the entire process you got no output. But the plug flow reactor was first of continuous reactors, where you put things in at one end and you got things out at the other end, which means that you had a continuous supply of products, and that was necessary and this is even before the beginning of the industrial age. So this was just before the beginning of the industrial age. And then what happened was the CSTR was discovered. CSTR was discovered a little after that, and that became a big breakthrough in whole of chemical reaction engineering, the discovery of CSTR. Okay. So CSTR discovery was done by two German scientists, Bodenstein and Wolgast, and I forget the year. I think it was around 19. Again, I think 1908 or 1909, something like that. Just around. I'll give you the years in the next class. I don't remember the years exactly. So, two German scientists. They were the one who discovered the CSTR. Now, this was published. Langmuir's paper, I remember, was published in a journal of American Chemical Society in 1908. I think I remember the journal. I'll give you all those references. I have these references with me, and I'll give you those in next class, and you can have a look at that. So, Bodenstein and Wolgast discovered the CSTR model, and that was quite a breakthrough. The reason that was a breakthrough is that, plug flow reactors are not always very useful because they are long, okay, and pipe kind of thing. So, essentially, a pipe kind of thing, and the problem with plug flow reactors, you don't have much control over the reactor, at least not in those times. What it meant was you only had control of what was going in, and you didn't really have control over what was happening inside. Whereas the CSTR is like a chamber, but you just allow things to enter and take out. So, you have a continuous supply of products, you have continuous input of reactants, and you have a lot of control on the system because you can stir it and raise temperatures, decrease pH, do whatever you want to do to the system. So, CSTR model was a huge breakthrough, and I am not sure if this is 1909, but around that time, Bodenstein and Wolgast model. So, that was a huge breakthrough. Now, what happened was that this discovery of Bodenstein and Wolgast was kind of didn't come out to the Western world all right. It didn't come out to the English speaking world all right. The reason being, this paper was published in German, and it was not translated at that point of time, and people didn't get to know about this. So, there was a lot of obscurity that this really happened, and a lot of other people tried to take credit for this, but that was not correct. And then Danckwerts also kind of took, not directly, but he was sort of trying to take credit for the CSTR model, but the model was first discovered by Bodenstein and Wolgast, and that's kind of well known. Now, the fourth thing, the important thing, is not the loop and the recycle reactor models, but something related to it is a three-dimensional convection diffusion reaction model. Okay. So, this is very important also. The reason this is important is the way we write the convection diffusion reaction model now, including the diffusion terms, the reaction terms, and the convection or the velocity terms out there. It was a matter of discovery. If you come to think of it, it didn't drop from heaven. Somebody had to discover it, and that was a path-breaking discovery in chemical engineering as well, in the whole of science as well, because that was the first time somebody showed that it is not enough to do some practical, these are good practical models, the CSTR model and the PFR model, but that was not enough. It was important to figure out what are the basics of the model, what really goes into it, and how does the convection term combine with the diffusion term and the reaction term, and so on. And the person who did it is a very famous scientist, German again, and do you have any idea? Let me try. What do you think? Yeah. So, I think this was in, I've forgotten the years, but this was in 1937, and this was a breakthrough paper, this Damkohler's paper, and this was again written in German, and I had a copy of this. I had a paper copy of this translated into English by one of my friends who is a German scientist. And so, this is a breakthrough paper, one of the greatest papers ever written in chemical engineering. The reason is that what he does, he reviews the whole history of chemical engineering, Damkohler, in 1937, and he was the one who gave credit to Bodenstein and Wolgast. He brought the CSTR model into light. So the CSTR model actually was discovered much before that, but it was Damkohler who brought this into light one more time, and it was kind of lost. And then he talked about the 3D convection diffusion reaction model. He talked about simplifications of it. He showed how the PFR model actually comes out of the 3D convection diffusion reaction model under certain circumstances or certain assumptions of axial diffusion, negligible and so on. So this was a breakthrough paper. The Damkohler's paper of 1937 was one of the greatest papers ever written in chemical reaction engineering, and it's a great review of everything that was going on. And so he talked about the axial dispersion model, not just the CSTR model, the axial dispersion model also. And then I think Danckwerts, he's one of the greatest known chemical engineering scientists. So Danckwerts, you probably use Danckwerts boundary condition a lot. So Danckwerts boundary condition is cited to 1951 or 52, something like that, 1951 say, to Danckwerts, but it essentially was not developed by Danckwerts. Okay, so now it's clear because we have reviewed the history of it, and it was first developed by Langmuir in 1908 in the ACS paper, and then by German people, some German scientists like Bodenstein and Wohlgast, and then again by Damkohler. So this was shown again and again. So Danckwerts boundary condition is Danckwerts used to take a lot of credit for this Danckwerts boundary condition, but it has now been shown that the Danckwerts boundary condition was not founded by Danckwerts, and I can give you the exact years. I'll bring the data in the next class. So we no longer call it the Danckwerts boundary condition, we just call it the flux type boundary condition. Okay. So it was there's a lot of credit given to Danckwerts, because that again boundary condition was a path breaking thing. Though we do not have, one thing you must know, that we do not have Danckwerts boundary condition or two-dimensional or three-dimensional problems in the 3D convection diffusion reaction model here. So we have the 3D convection diffusion reaction model, and we are not aware of what the entrance boundary condition, flux type entrance boundary condition for a three-dimensional system is. Till now we are not aware of. Okay. But what we are aware of is, if you write a 1D model of this or a 2D model of this, how to write the boundary condition. Because what happens in a 3D is, because as soon as you take the reactor like this, say, okay, this is a reactor cross section and it goes like this. So as soon as it's 1D or 2D, it's all fine, but as soon as the theta dimension comes in like this whole boundary condition can change, because there could be a lot of effects in the theta direction. So we're still not aware, but still this was a breakthrough condition, the flux type boundary condition. The reason that it was a breakthrough condition was minus d del c, this is boundary condition, right, equals v times c minus c naught, like this, or c minus c. That what this said was that whatever is coming in at the entrance, whatever is coming in because of, what does the flux type boundary condition mean? It says that whatever is coming in at the entrance because of convection equals what goes in because of diffusion plus convection, right. So that is the boundary condition. So if you look over here, then you get minus c del c del x plus, so if you put a plus over here, then plus v times c in equals v times c in. Yeah. So this is, yeah, just take this form. So this is what is coming in, v times c in, okay, the velocity times concentration. I'll pull this a little to the middle. Yeah, this is what is coming into the system, and what is going out is diffusion plus convection, fine. So this is so there shouldn't be any confusion about this, because this is a very straightforward system. So this is the boundary condition we have, the Danckwerts boundary condition. So essentially, so I'll do a review, a little bit of more review of what is going on in this system for the reactors. But what I wanted to tell you is that there's these 4 different kinds of reactors. Let me bring that page one more time. Yeah. So there's 4 different kinds of reactors: the batch reactor, the plug flow reactor, the continuous stirred tank reactor, and the loop reactor. And there is a certain history to it. And as I said, this is the earliest reactor at the dawn of human civilization. The plug flow reactor was around 1900, a little before that also, maybe 1800 and so on, before the start of the industrial age. And the continuous stirred tank reactor was a huge breakthrough because most of the industries shifted to the continuous stirred tank reactor because of of the advantages of it. It was smaller, it was easy to handle, it was easy to control, easy to manipulate, and still you have a continuous product and a supply of products. Okay, and then came the recycle or the loop reactors. Can you tell me that where are these recycle or loop reactors most used? Which kind of industry? Yeah, that is one. And what else? Yeah. So this is actually recycle. Loop is not used so much in effluent treatment, and recycle is used in effluent treatment, and loop is used in polymerization. Okay. So do you know the difference between a loop reactor and a recycle reactor? Okay. So the recycle reactor is something like this. So you have this is a reactor, say your main reactor. Okay, this is going out, and this is the recycle ratio is R, say this is the recycle reactor. Is clear? So some things going out, things coming in, things going out, and there is a there is a recycle out here. And loop reactor is little different. Okay, this is how it is. So this is my reactor. Okay, and this is the entrance, this is the exit. Do you see the difference? You see the difference between the loop reactor and the recycle reactor. The difference and the similarity. Similarity is that things are being recycled in both cases, but in a recycle reactor, the reactor is one straight thing, and there is a little recycle going out. In the loop reactor, the reactor itself is a recycle. So the major part of it, what is the major difference? In the recycle reactor, only a small fraction is being recycled. Here in the loop reactor, a large fraction is being recycled. Okay. Now that wouldn't work with this kind of setup. If you want to recycle a large fraction of it, that wouldn't work with this kind of setup. So you want to recycle a large fraction of it, you put this kind of setup where everything goes around in loops and loops. You put a little bit in, take a little bit out, but rest of the thing goes in again and again. Why are these recycle and loop reactors used? Especially for reactions which are very no, that's not the point. Yeah, reactions which are very slow or low conversion reactions, so that you tend to send them again and again and again to make it work. So these are the different kinds of reactors that we use, and again, for biological systems we can use all of these reactors, batch and plug flow and continuous and even recycle reactors. There is nothing stopping us from doing the same thing. But when you use something like a recycled reactor, it's a little hard because you have the cells within it, and it's hard to recycle with the cells without killing the cells, slightly hard. But you can, so these are in biological systems, these continuous CSTRs are called chemostats. Okay. And the batch reactor is called the batch reactor, and the plug flow is much. So what I'll do is, this history is interesting, but I didn't remember that I should give the history today. So I don't have all the years. So I'll do a quick review of the history in the next class and give you all the exact dates and the papers. I have the citations to all the papers that were being written, and it's very interesting to be aware of the history of a process that we are a part of, because unless I think this is something you probably are not aware of, what the history of these reactors are. And so there is a Dankor's boundary condition, then there is the axial dispersion model, and and you are also aware of the surface renewal theory, right? So surface renewal theory, so that there is a history to that also. So anyway, so these are some of the things I'll quickly discuss in the next class. So let's go back to what we were doing without, that was a digression, I think. So what we're doing is the monode model, and what I asked you is that this is where it started. Are these are the monod growth model. Let's forget this, just look at this. So dx dt equals mu x, that's my monod growth model for x. What I asked you, is this equation valid for all kinds of reactors? And that is why I digressed and started talking about the different kinds of reactors. Which kind of reactor is this model valid for? The way I have written it here, you should be able to tell this now. What about other reactors? Yeah, because the batch reactor is the only kind of reactor which does not have a which is not a continuous reactor. So if you have a continuous reactor, then obviously there have to be input and output terms. So it cannot, dx dt cannot be written in just a reaction rate. So this is something I want you to be very clear that. So when it is a batch reactor, because I see students keep doing it despite telling them again and again. So dx dt equal to reaction rate only and only for a batch reactor. For all other kinds of reactors, dx dt is not just reaction rate, but there are inputs and output terms that have to be added in. So do not ever write dx dt equals reaction rate unless it's a batch reactor. Fine. So this is, I mean, I tell students, but I still keep seeing these mistakes on the answer sheets. So a very straightforward thing, but you still need to remember it. So in similar vein, we can write the growth model, the dsdt, this again for batch reactor, for the substrate. So x is my cell and s is my substrate, and the reaction rate is the same over here, except there is a negative term outside because substrate is being consumed in the reaction, whereas cells are being generated. And why is this y excess? Because we discussed this in the last class. Y is the yield of x per unit mole of S. Okay. So here we have used this as a, this is my yield, reaction rate for x. So you have to convert that into S. If you are doing a molar balance for S, then the yield of x per unit volume of S, if that is y, then 1 over y is the yield of S per unit x, right. So you just multiply that by that number, fine. So then this is my basic equation for a batch reactor, and what we do now is that we try to express x in terms of S. Okay. So when we try to do that, so what do you see over here? How do I, if I ask you to manipulate this system, how would you do that? Tell me quickly. If these two equations are there, forget this. If I ask you to manipulate so that you get x in terms of S, what would be the first step? I discussed this in this earlier in this lecture, I think, when we are doing enzymes. It's something called the method of invariance. What is that? So let's see. So my dx dt, yeah, no, don't divide it. You just use what is known as the method of invariance. So dx dt equals mu x, ds dt equals minus 1 over y times mu x. So what you do is multiply the first equation by y, multiply by y, and then add. Fine. So multiply this equation by y and then add. So then you get dx dt plus y times ds dt equals 0, y being a constant. Fine. So ddt of x plus ys equals 0. Fine. Then what? So x plus yx over s times s equals x naught plus y x over s naught. Okay. Now if there is no, I think what we are using here, yeah, we still have x naught here. So so then x could be expressed as x naught plus y x over s s naught minus s. Fine. So, my ds dt can be now written as minus 1 over y x over s mu max s x naught y x over s naught minus s k s plus s, fine. And though this is nonlinear, we can still integrate it, because it looks like we can use partial fractions to integrate this, right? Appears to me, yeah, because just quadratic on the numerator and linear on the denominator. So, I think we can use partial fractions to integrate this, fine. So, this is called the, what is this called? This is called the method of variance, and you shouldn't forget this, because this is a common trick. So, whenever you see a nonlinearity out there, and here for example, let us see. So, here here for example, whenever you see a nonlinearity out there, this is a nonlinearity, and you see the same nonlinearity in both equations, just a constant difference of constants, just manipulate the constant, add them up, and get rid of all nonlinearities, and then you will get a ddt of of a certain combination of two of the variables, any combination, but certain combinations of two of the variables to be a 0. And where have I taught this? Where else can we talk about this? Is very straightforward. Where else can we talk about something like this? Which equation is on the screen? Which equation? First one, no. First one means which one? Huh? R is nonlinear, yes. So, this equation, the temperature equation out here, and this equation out here, the last equation here and the temperature equation. So, let me show you. Q, typically Q and W are 0, let us assume Q and W. So, W is the work done, Q is the amount of heat generated apart from reaction in the system. So, these are typically 0. Even if they are not 0, we can still take care of them. I mean, it is not a problem. Like if you want, I can still assume it to be non-zero, and still we can do it, because it is a constant. So, let me show you. So, dCi dt equals R, okay, Ci Cj, and rho Cp dt equals minus delta Hr times R Ci Cj plus, let us say, Q over V, okay, Q over V is a constant. So, what do you do now? You multiply the first equation by, I think there is a, there is a sign mistake. I think it should be minus of minus delta Hr. If that is positive, then that is fine, I think, it should be minus of minus delta Hr, I think, minus of minus delta Hr out here, this, So, what do? You multiply the first equation by minus delta Hr. So, multiply by minus delta Hr and add, and what you get is minus delta Hr plus times Ci plus rho Cp T, the whole thing ddt of that equals Q over V, right? Q over V. So, this is a constant, Q over V, even if it is there, it is a constant. So, you can integrate this straight away, and what you will get is, you will get a relationship between, so, Ci minus delta Hr Ci plus rho Cpt equals Q over V times T plus constant. You know what your concentration was at C equals T, time equals 0, you know what your temperature was. So, you can evaluate the constant out here. Now, how does it help? The way it helps is, because see R, how is R typically, R Ci Cj T, say for a first order reaction, it is typically Ci times exponential minus E over RT, right. So, what you can do is you can replace the C, because C is linear out here, you can replace the C by what you got over here. So, C you can write as Q over V times T plus, let us say beta 1 is a constant, minus rho Cp T divided by minus delta HR. Okay. So, you can replace that out here. How does it help? Here when it is replaced, now it becomes a equation in T alone, and you can go and straight ahead solve it, though it is still a nonlinear equation. See, there is no escape from the nonlinearity. If it is a nonlinear equation, however you solve it, it is a nonlinear equation, but the advantage is that you have converted the nonlinearity of two equations to a nonlinearity of single equation with just one variable, and that is much easier to solve any day than two nonlinear. I mean, one nonlinear equation is obviously half as easy to solve than two nonlinear equations. So, that, and this is a method that you should always keep in mind. This is the method of invariance, because always when you get a system of equations which are nonlinear and you cannot solve them individually or together also, just see how you can manipulate these two equations. If when can you manipulate these two equations? If the same nonlinearity occurs in both the equations. Okay, is applicable if same nonlinearity in both. Okay. Fine. So, why I am saying all this is because we are going to use some of this in the latter part of the course. So, so anyhow, so using the method of non-invariance, this is what we got. We just did the calculation. I think we have it out here. Let us see. Yeah. So, here on the page, if you see, so we did this, and the initial conditions are x equals x naught at t equals 0 and s equals s naught. Now, this we have converted into a equation in s alone, and we can integrate this as we said. So, this is the invariance, and we walked through all of this. So, I think I can skip that, right. So, on integration, this is what you get. Okay. This is the whole thing that you got. And how do you get this? Using, as I said, just using partial fractions from this side, you know, just take it to the denominator, use the partial fraction, then you will get exponential for both cases, and this is the solution you got. So, here x naught is the cell concentration at time t equals 0, and S naught is the substrate concentration at time t equals 0. There is a faux pas here, you know, and what is that? The faux pas is that look at the equation. If x naught is 0, then this solution does not hold. So, you have to go back and resolve it, because S naught is most typically might be 0, you know, not most typically, but might be 0. There might be cases when you take a feed which has no cell. I mean, not all times, but there could be times when you take a feed which has no cells at all, or very negligible concentration of cell, then this will blow up. So, you just need to go back and put that into the equation and then solve it, rather than solve it and put it into the solution. Okay. So, if the product that is formed from a culture, that is from the growth model that we give, and there are some other sources of cell formation apart from the culture, then what will you do? It's straightforward. What is the growth model? The growth model is dx dt equals mu x. So, what will you do in that case is just use a dx dt equals mu x plus beta x, okay, where beta is from non-culture sources. So, unlike mu, which is the function of S substrate, beta is not going to be a function of S, it is simply going to be a constant, but you will have a non-culture source. So, then you can use something like this. So, del P del T, the product formation would be some alpha times mu times S x over S plus k plus S, that is the monod growth model, plus beta x, and beta being a constant. Okay. And how do you think this will affect the product formation? It will obviously increase, but in which way? in qualitatively which way it will increase. Obviously it will increase, not to say that. Yes, slope would definitely change, but what would more than that change is the saturation, because say this reaches a level of saturation, okay, because of the monod growth model there is a level of saturation, but in this the level of saturation would change. So this is how it looks like. See, so the product that you get, so this is a product, by the way, so slightly different from the cell. So so the cells are, cell culture you are doing, and because of the cells a product is being formed. I mean, I probably didn't explain it properly. So this is different from what we did before. So the cell is being produced X, but because of the cell a product is being formed which has slope beta. So the substrate is here just like before, because the substrate is being consumed only in the cell formation. So exactly the same way as before. The negative of monod growth kinetics, as you can see, just the thing flipped around, because whatever is taken, the substrate is being taken up, consumed and not formed. So it's exactly the monod growth kinetics flipped around. The cells, again you see there is a monod growth kinetic, the formation of the cell, okay, but the product formation is not going to saturate out, as I said, because there is a term which is a constant and it goes linearly increases. Fine.
So the dependence on x of the second term, that is beta x, is it always linear, beta into x?
It doesn't have to be linear, because it depends on the product formation, but it could be it could be even beta x square, at most, but it's not going to be exponential or something. It doesn't have to be linear. See, what is essentially happening, what we are trying to say over here, the cells are formed and the cells lead to some other products, okay. Now what that reaction be? That could be a first order reaction, that could be a second order reaction, it can be a third order reaction or any higher order. It cannot be an exponential dependence. One possibility is that the exponential depend on temperature, that is a possibility. So beta, for example, beta x could be such that some beta naught exponential minus a over RT times x, that is a possibility, okay. So that is one possibility, or you can have, beta itself could be, it go as beta 1 or beta naught times x, so in which case it could be a second order. So anyhow, so all we are trying to say is that the products that are formed, it is not going to saturate out, whereas the cell formation could saturate out, and the substrate consumption could go on, and it can reach 0, so substrate concentration, but the product formation will go, okay. So I think the next thing that we'll start is, we don't have a lot of time today, but we'll just give you a brief overview, is the concept of death of cells. So we had been looking at the growth of cells, but what happens when there is a death of cells? And the answer is, would any of you want to tell me? It's very similar to what we did just now. Yeah, so it could be minus beta kind of thing. So if you remember, do you remember that we did the microbial growth models, and we talked about, I think I have the slide with me and I can even go in there. Let's see, yeah, here. So here, we talked about the, here. You remember this, right? So this is a phase. This is the exponential growth phase, right? And we modeled the exponential growth phase using this, and then some saturation and all that. And then the stationary phase. The stationary phase was when the growth of cells equal to the death of cells, and the death phase is one when there's growth completely stops and it's only death of cells. Fine. So this is exactly what we are trying to model over here. So this is the growth, so the stationary phase and the death phase. So that is what we are trying to model over here now. So dx dt equals mu x minus k x. Why do I put the v? V is for some live cells, okay, just for live cells. So k is going to be, remember, k is going to be a constant, okay. K is not dependent on the substrate, whereas mu is dependent on the substrate, okay. X dt equals kv, d being dead cells, right. And I went on and talked about the whole experiment, if you remember, of doing another microscope and checking how to check the number of dead cells. Do you remember all that? So this is a very natural corollary of the entire incubation process, and there is no running away from the fact that there are always going to be a lot of dead cells when you deal with them. So again, you see that we do some kind of invariance out here. We say the total number of cells that you have in the system, like we did in the last class, is not a constant, but it's increasing with time or decreasing with time, whatever is this is that, and that is mu times xv. Okay, fine. So xv is xv naught times exponential mu minus k times t, right from the first equation, very straightforward. And xt is this. How do you get this? So you just solve for xv, put it up into this equation, and then you can directly solve for xt. So this is what we get here. So this this number, you know, it depends. Now what does it depend on? Like you see, whether there is going to be a stationary phase or whether it is going to be a decay. So how do you define that? When mu is very close to k, for example, it is more or less in the stationary phase, because this term is kind of 0 and you know this term is close to 1, so it will be a constant. When mu is less than k, then it starts to decay in the death phase. So typically in the first part of it, the mu is much larger than k, so it keeps increasing, and then mu is, when it's close to k, then it's in the stationary phase, and then when it goes to decay. So here is a plot for that. Yeah, so here is a plot. So in this phase, mu is greater than k, much greater than k. In this phase, mu is more or less close to k, so as a result there is more or less constant, and this phase mu is much less than k. Okay, so I think we'll stop. There's something else in the next slide. Is, yeah, next slide we go into the ideal CSTR models. I think we'll stop here with the death of cells, and that concludes everything to do with the batch reactor model, and next class we will start the chemostat, but I will try to remember to bring the years and the references for the history, because that is a pretty interesting thing, I think. So is there any question before we conclude in today's lecture? Okay, then we will stop here today and we will continue with the CSTR in the next lecture.